name is Jared Lettery, and welcome to the AI Academy. I'd like to introduce Dr. Ignacio Medrano, who will be our next speaker. By training, Dr. Medrano is a neurologist, and what better background than a neurologist to explain neural networks. He's going to talk about precision in AI decision-making, and I'll look forward to his comments. This will influence ultimately our understanding of how we're applying AI in the field of assisted reproductive technologies. Thank you very much for participating, Dr. Medrano.
Hello, everyone. Thank you for having me here. My name is Ignacio Medrano. I am a neurologist, so nothing to do with fertility, but you will see that there is something related to what I do. 8 years ago, I decided to dedicate my life to try to bring artificial intelligence as soon as possible into healthcare and medicine. And that's what I did by starting two AI companies, Savannah and Mendelian. For sure, you shouldn't believe a word of what I'm going to say. You should probably go and check by yourself. But at least I'm going to give you an angle of a doctor, a pure clinician that got into this world, and how I see AI, how I understand it from my, let's say, non-educated mathematical mind, and how I try to apply it to actual real patients every day. So the best way I found along these years to try to explain what it is, the concept of AI, machine learning, and so on, is Google Translate. There are other ways of doing it, maybe with chess, maybe with self-driving cars, but this one is a good one. Because if you think about it, it translates all the languages in the world, this tool, but it doesn't know anything about them. That doesn't know anything about syntaxes, about grammar, but it translates all the languages. And how can that be? Well, the reason is that it's not that different compared to what I have at home when my son is learning how to speak. The reality is that biological systems, in general, we don't learn by rules, but we learn by seeing cases, by examples. That's what we also call clinical intuition, and it's applied to so many things in our lives. And what happened until quite recently is that when we were to create computers, instead of teaching them the way we learn by cases, we taught them by rules. And learning by rules is okay. It solves a few problems, but it's not enough, because the problem with learning by rules is that when a new problem comes that the machine has never seen before, it cannot solve it. While biological systems and humans, if we learn the pattern, that's what we call pattern recognition. Sometimes we also call it intuition. Sometimes we call it heuristics. It's all the same. What is good is that a new case, as long as we can allocate it and put it in the same place, then we're good to solve it. So Google Translate, it works that way. It learns by seeing cases. That's how it learns the languages. And that is interesting because it can solve new problems, translate new things, even when it's the first time it's seen it, with a certain level of accuracy that is probably not perfect, but good enough so that we use it every day. And so that concept of by which around 2013, 2014, maybe in California, maybe in Boston, maybe in Tel Aviv, in London, some people thought, why don't we start treating computers like biological systems, and we start teaching them instead of programming them, is what we call machine learning. It's actually not from 2013, 2014. It's something that appeared in the 50s, but it became mainstream and popular and exploded for some reasons, for some big data reasons, the internet basically, and something like 10 years ago, not much more than that. And it's really revolutionizing the way we understand knowledge. But once more, I will review this and then we'll get into practice. But the idea is, instead of giving it the rules, we give it a set of solved problems, so that by itself, that's the key, it can infer the rules like children do. What's a table? Table is this, not because it has 4 legs and so on, but because I've seen many, and then I know what a table is. And that means that I can now look at a new table, even when it's the first time in my life, I know it's a table. And that's anticipation of unseen problems. That is what machine learning is. And that is what is making artificial intelligence so important in our lives these days. That's why everybody's talking about it. I won't get into fancy names like, what's deep learning. Some people can explain that better than I can. I don't think that's very interesting for clinicians, to be honest. But the idea is that when companies, institutions governments, all, even football teams, everything, when they realize about the power of training machines to anticipate new problems, they start using it and they start disrupting their worlds by applying this new technology. So there you have Amazon, which wasn't the best retail company at all, but it has so much data, so many cases from the internet that it's able to say, okay, I'll look at this, I'll create this machine learning system, and then now I know who and how and when is going to purchase something, and I become practically #1 company in the world. And then Netflix would be another nice example. It wasn't the Columbia or the Warners or Disney. It wasn't one of the best filmmakers in the world, but in a short period of time, it had so much data to analyze that it's able to predict who and how and when is going to like something, a show or something. And that's how they become #1 filmmakers in the world, and so on and so on. So with the stock market, 98% of the transactions are now done by AI systems. It's crazy to try to do it as a human. And in politics, as we all know, governments are using this kind of tools these days to change the vote of people by inserting news, inserting social networks, and that is all done by machine learning systems. And we could go on and on with examples in sports, in cooking, and fight against poverty. But machine learning is simply going field by field, setting new rules. It's happening. It's here. The last 3-4 years, it's in the newspapers, and I think it's already quite obvious. Now, the thing is, what about in healthcare? What about in medicine? Well, in 2014, people said it should come. Maybe it will come. I don't know if it will come. Now it's kind of past. It's not the future anymore. You go to PubMed.com. You write machine learning, you're going to find that it's really exponential, the number of studies that are using AI these days across all kinds of pathologies, all kinds of specialties. But maybe what you're not going to see that often is this distinction, where these machines at the end of the day, which ultimately what they can do is looking at the number of variables that we as humans cannot look at, because they're simply they have too many dimensions. Let's call it like that. So classical statistics, classical regression won't work here. This is statistics powered by computing. So maybe we can call it like that. So what they basically can do is classify things better than we can. For example, facial recognition. Our visual cortex would never be able to classify faces the way these machine learning systems can, or predicting, forecasting something before it happens, where we humans are especially bad at. But there are many cases. Here is a nice one by taking pictures, so solve problems of people that were successful as models, as fashion models. Now with a machine learning system, you can take pictures of teenagers and you can guess who is going to make it as a fashion model. And that's how the agencies now invest their money in the right people, not because there are human experts there, but because there are machine learning systems labeling who will make it or not. How does it work? We don't know. It's pixels, so that's where we have to confront the black box example, the black box situation that we'll talk about for a few seconds later. But the idea is that it can classify or forecast. And the same would apply to healthcare. You're going to see in the newspapers, in the media, you're going to see in many cases talking about machine learning systems classifying, so properly putting things in the right box. Like, for example, this very famous Google DeepMind example in the UK that in 2016 was able to classify better than ophthalmologists who had a diabetic retinopathy by doing a fundoscopy. And then it can do the same with other diseases. But then you have forecasting. You have the ability to say, not who has it now, but who will have it, who will have a diabetic retinopathy, or as we can see in this nature, who by looking at fundoscopy will have higher cardiovascular risk. And that's quite remarkable. The day I saw that, it kind of changed the way I saw this whole world, because think about it, there's not one mention in the scientific literature in medicine to the fact that by looking at the eye, the retina of someone, you can guess the cardiovascular risk of someone. But a machine can do it because it can see correlations, associations among variables that we cannot as humans, and that we cannot with our classical normal statistics. But this new mathematics, this machine learning mathematics, can do it. And the moment you understand that it's very powerful, because how many biomarkers, how many everything with everything these machines are going to be able to correlate, and therefore how much it is going to allow us to do actual precision medicine, meaning finding by looking at historical data, which is the particular phenotype, the particular cluster that our patient has that is going to respond to something. That is what is impressive. So when I look at machine learning in medicine, most people will go to the, the machine that classifies, the machine that diagnoses. Managers are interested in this, government, investors, all kind of cool apps around this world. That's okay. Maybe it saves time and money. It's very efficient. But where I'm particularly interested as a clinician, as a researcher, is in the other part, in being able to stratify the risk of something before it happens. And as I said, in the past, we already did risk stratification. You have Framingham, but that's maybe 100 variables, the same variables that are already biased and pre-selected by the human mind that don't refresh themselves. So it's very different to doing it this way. So it's not the concept that changes, it's the way we do it that makes it much more in real time. And in this regard, the next thing that maybe we all think about when we are talking about these possibilities is in the idea that by looking at images, you can predict things, you can create things. So if you look at that face of that woman, she doesn't exist. So that's a fake. That's created by a machine learning system that learned how human faces are by looking at previous cases and was able to create a fully new and non-existent human face. You can do as many as you want if you enter this website. And this is used for many purposes. For example, to cheat us on Twitter by creating fake profiles of Russian fellows that want our money for some reason. But even when that is happening in our daily life all around, that is the kind of technology that we can use, of course, for our own field. And we can then feed these machine learning systems with this kind of technology, which is a type of machine learning, and being able to predict things that otherwise we wouldn't be able to predict with our classical methods. And that's already happening. Yeah, I'm sure you're seeing many cases, and you're going to see along this course. I mean, if you go type fertility, even for a completely non-expert like me, you type fertility into PubMed, you're going to find all kinds of articles where someone takes some image and gives it to the machine, and it's able to predict something better than our previous standard. And you can use this for so many reasons in the lab. And I guess that is already part of the standard. If you're not there, probably you're way behind compared to the top providers of this type of treatments that are already jumping every month into this machine learning thing. But something that maybe I wanted to remark today is that even when in 2019, the fact that machines match humans in image-based diagnosis, as Lancet said, even when, if you go to the approvals of AI systems in healthcare by the FDA in the last 3-4 years, the majority of them are going to be image-based. Images is not everything. Images is just one data layer, but there are many data layers that you can give to that machine learning system. So you can do that with proteins, and you can do that with genomics, and you can do that with, with drugs and molecules and transcriptomics and all kinds of information. And the more multi-data layer, multi-model you do it, the better it's going to predict. That's quite obvious, right? So that's where I work. I always say that if you get invited to give a lesson, to give a talk, if you only talk about what you do, that's not very elegant. But at the same time, if you don't talk about what you do, then what do you do aside of being someone that gives that gives talks? Well, this is what I do. This is my project. I started thinking a few years ago when I was at the hospital. I mean, this is going to happen. Machine learning, it's going to be a reality. AI, of course, it's inevitable, and there are going to be many data layers. But what about that data layer that I see every day in my reality that has a lot of information? And actually, I would say that without that one, it's very difficult to have good practical cases. Maybe some cases with images, but you need it. I'm talking about the clinical variables, and I'm talking about the medical records, where we write down everything about the patients. Incredible source of information that we can give to the machine learning systems. Now, the problem until very recently is that they were paper-based, they were handwritten, so there was nothing we could do. But then we digitized them. And now that they're digital, apparently we could give that to the ML machine learning systems, and that should work. But the thing is that there's another problem. The problem, and it depends a bit on where you are working, but in some cases, a significant amount of the information that you write is not structured, it's unstructured. So it's the outcomes are there, but they are in free text. And that happens in histopathology reports, in laboratory reports, radiology reports, that happens in discharge reports with all kinds of internal medicine patients, that happens in oncology with the toxicity and the results of the drugs and immunotherapies. That's all around. So free text narratives is a big thing. And then we have something that is called natural language processing, which is the ability, that technique inside informatics that is able to translate language, human language narratives into structured databases, ones and zeros, that then we can give to the machine learning systems. And by the way, I don't want to make it too complicated, but that natural language processing part, at the same time, it also uses in itself some kind of machine learning, so that computational linguistics is better than the traditional one. So what about if we start doing that, if we are able to take care of acronyms, copy paste, duplicities, proper names and common names, everything that is there, and we're able to transform all that into databases that then get harmonized across sites and even languages. And then we can have a kind of evaluation tool with which we can check that what extracted was correct. So you can look at actual a random sample of fragments of text, and as an expert, you can say, okay, here's correct, here not, and you train it in a way. And then you're ready to say that now you have a machine that is able to create registries automatically or from the original EMR systems with no data collection. So no double data entry, no CRFs, these things, if you've been into clinical trials, that can be done by a machine now automatically across sites, across languages, and it's now a reality, the concept of real world evidence or registries created by artificial intelligence systems by pulling the information from medical record systems around the world. That's something that's what I do. That's what I created with my team since 8 years ago. And of course, it can be applied to any field, any pathology. Oncology is quite important, obviously, because there's a lot of research there, but of course, it can be applied to fertility. So maybe the message here is, aside from the fact that I'm doing this, but with me or with any other, there is something you can do beyond the lab, more on the clinical side with that information that you generate every day. These are just some predictive use cases and fertility that we are looking at in a way or other. The most obvious one, which is increasing the success per line of treatment or phenotype by putting those variables into that system, which is not a regression, but can look at associations that we cannot. But of course, you can predict the stability of the follicle growth so that you can maybe save a few visits, or you can have a higher accuracy on the number of donor eggs that you have to use for a certain treatment, depending on the phenotype of the person. So there are as many clinical questions as you want. They can have a great, let's say, understanding between the more cost-efficient part of sites and the clinical side of things. And maybe those are things that you want to consider. If that's the case, I'm super happy to talk about them offline. But I was telling a story, and the story is that we somehow in the past moved from a symptoms-based or intuitive medicine into a patterns-based medicine, or evidence-based, we call it. But now we're doing something else. We're kind of jumping into this algorithms-based medicine, or helped by AI medicine, you want to call it like that. The idea is that it's already happening, and that, of course, it's not perfect, right? So it has problems and limitations, and I want to talk about them for a few minutes. So when you look at that, algorithm from Google DeepMind, which is able to look at the retinas, the fundoscopy, and it's able to predict who has a diabetic retinopathy. And as you know, that got approved by the FDA. So that's part of our reality. The same one, even when now you have it in some grocery stores in the United States, the same algorithm, you put it in Indonesia and India, big failure. It didn't work. Why? What's the reason for that? Well, humans. I mean, acquisition of images, the way you use it. Some people call it human in the loop. Like, you have to design the systems to an actual clinical reality. We know a lot about this, no? You know, about clinical trials and then the reality. So this is not going to be different. And in that regard, Gary Collins and other colleagues are now in charge of reporting what are the problems of, you know, with the actual application of AI systems in healthcare. And those are the ones that we have to consider. And at the end of the day, what we have is a checklist, a set of things that if you do them properly, then it's much more likely that it works. We're talking about validation. We're talking about, did you save a set of patients to check it retrospectively and then prospectively? Are we talking about, you know, randomizing? So the kind of rules that you have to follow in science, so that it's not just algorithms that you create with a machine and you're good to go. It's not like that. And the more technical people come to our world, the more they realize that some rules are to be followed. Those rules are you know, fighting to be the one rule, the one standard. So I don't know if it's going to be Decide AI or Minimar or Tripod. In Savannah, in my company, we use Tripod, but it doesn't matter. They're basically, they all say the same. The idea is that you have to follow a set of scientific rules. Otherwise, it's not gonna be good enough. And of course, there are other problems that we're confronting. So when we deliver a new predictive result, doesn't matter if it's in Crohn's disease or in cancer or infertility. These days, we're working with hospitals in the US, in the UK, and in Spain and France. So when we do this, we find first this, you know, this situation that we have to confront, that we have to follow the right checklist to get published in good journals. That's one thing. And how that gets pushed into the clinical guidelines. We're finally doing that. But there's another problem aside from quality, which is what we could call interpretability, which is if you make a tool that is very nice mathematically, but doctors don't understand, or the managers of a hospital don't understand, they don't know how to use it, they're not going to use it. So in that regard, we have some nice examples like this one from you know, a few hospitals. I think it was led by the University of Duke. And so with machine learning, they found which were the variables and their weights that you had to look at to be able to predict the risk of seizure, so that you wouldn't put too much money into EEG in the intensive care unit. Classical clinical problem that no one had solved, but they kind of solved it with this new system. Now, they were smart enough, and this was already a few years ago, to say, look, we have to transform this into something that doctors like, which is a scorecard. So ones and zeros, and then you get a risk, and people use those things. Because if you give them a, you know, mathematical model that talks about things like entropies, which is the kind of things that you see when you look at machine learning results, what data scientists give you, as a doctor, you're like, come on, I don't know. But if you translate it into this, you make it look like a regression without being a regression. That's at the end of the day what you're doing. It's like a trick. Then people use it because they look at the variables and they have an opinion and they say, no, but this one, diabetes, I'm not going to use it because of this and this. And so if you do that, then people use it, and they proved it. So that's something that maybe we have to consider. And maybe one last thing would be, of course, you know, the ethical part of all this. So this was a bit before the pandemic, and we received this article from China in JAMA, and it said, look, by looking at the faces of the citizens, I can say who will have an atrial fibrillation. But what I like is what the editor of JAMA said. He said, let's be careful, because, you know, today it's face and arrhythmia, but tomorrow it's going to be what? You know, pictures and psychosis, intellectual level sexual. So whatever we do, we have to do it with a very protocolized, ethical committee, IRB approved definition. Otherwise, it can be a problem. Not, let's not mention, the insurance and all these things. So it's quite obvious, but we have to do it. Otherwise, people are going to reject this, and we're going to miss a great opportunity for patients. Maybe the one last thing I can add is that you can get trained in this. People are thinking about this. The UK, with their national health system, they already published a guide where they tell their managers, look, if you're going to acquire AI systems, these are the things that you have to look at to be sure that no one's bullshitting you, so that you can use it. And then on the more scientific side of things, if you are a reader of these kind of algorithms, maybe you want to read if they're properly created, and you can learn how to do that by being, by having the right critical tool. So that's just one article that shows you a bit of the way. And yeah, this is what I learned along these years. The majority of the AI systems, they succeed or not if and when they have the right clinical question. So it's normally, thankfully, not a problem of privacy anymore. We're solving that quite well. We already know what de-identified information means, IRB approvals. So that kind of things is quite solved. Informed consent is normally not needed if you de-identify properly. So we already know. And also, of course, the economical part is there, but in the majority of cases, if you do things well, this is very cost efficient. You make much more money than you spend. So the problem is not any of those. The projects that fail are the ones where there's not one mind that understands the field and says this and not these other 10, but this one is the clinical problem that I need to solve with this machine learning system. And that if I solve it, I'm going to help patients and I'm going to have a more efficient way of attending them. That's what I've seen. So the right clinical question, because as Picasso, the Spanish painter, said a few years ago, already in black and white, he said, computers, they're useless. They just give you answers. So with that and my 120 people from Savannah, which in a way are here with me today, because otherwise I wouldn't be here. I want to leave you, and I hope this was interesting and useful, and I will be super open to follow up offline and to welcome you, if you're not there yet, into the tribe of doctors that at some point realized that AI was not just one more fancy thing, but a real tool that came to stay. So thank you very much.